Alrighty, all right, everybody can see. Can y'all see my screen?
Yeah.
Alrighty, well, yeah, as Jack said, hi everybody. I am wrong button. I am Cody Hatfield. I am a part of the Katin Kollective, and I'm here to talk to you about a little thing that we came up with called Degenerative Art using Python and machine learning. This is going to be an exploration on leveraging improperly trained neural networks so that we can get them to do some pretty cool things. Again, this is brought to you by the Katin Kollective. They help sort of sponsor this research, and I'll talk about them a little bit more towards the end of the lecture. A basic outline. We're just going to go over what we mean by degenerative art, as well as a short introduction to neural networks. We're going to explain how something called gradient descent works, which is an integral part of neural networks. Some basic image operations we can do with neural networks, as well as generalization as it applies to the topic of machine learning. We will introduce the music video project that sort of spawned this entire lecture, as well as go over the architecture of the neural networks that were used in that project. We'll perform a final analysis of those neural networks and then draw some conclusions. And then we'll have a short, a little bit of a question and answer session at the end, if anyone's curious about, what methodology we used. So to begin with, I want to talk about what is degenerative art. What degenerative generally means, it's defined as this state of deterioration, of something losing functionality or becoming not as good at something. So degenerative art is a type of glitch art. It's specifically created by malfunctioning neural networks. Because you see, the inherent structure of neural networks makes them really good at pattern recognition and pattern generation. And as a result of that, they tend to, even when they're malfunctioning, even when they're not acting correctly, neural networks tend to still, they still have some sort of structure in the output that they create. There's still a very clear, discernible pattern. You need to compare this or contrast it with pure noise, which you can see in this square right here as an example of pure noise. It's just random, there's no structure, there's no rhyme, there's no reason behind it. And so even when neural networks, when they malfunction, they generally don't tend to go into this sort of pure noise direction. They still have some sort of structure behind them. So this term, degenerative art, is not a description so much of how the art looks, but rather how it's made. Now, neural networks, generally, they're really good at generating an output by transforming an input that you give it. You can think of it as whenever you give a set of numbers to a neural network, that each of those numbers in this first ring of nodes right here gets multiplied by a weight. So each of these orange arrows represents a weight that this node is multiplied by. And once it's multiplied by that weight, it's sent to the next set of nodes in the network. And in that next set of nodes, it takes all of the previous weighted values that have been given to it, and then it sums them together, and that new value becomes the value of this node in the network, which it then passes on to the next set of nodes along these weighted edges. And this process repeats until you get to the end of the network, which is the output layer. So the question becomes, what then should the weights be? How do we decide what these weights are so that we can transform the input that we're given into a desired output? We need a way to accurately set the weights of the network. So this is where machine learning comes in. Machine learning is defined as the study of computer algorithms that improve automatically through experience. And the general idea here is that when we can show a neural network a whole bunch of data of when you're given this kind of input, we want to have this kind of output. And the neural network will automatically update itself and change its weights so that it will give us the desired output that we want. And that's why it falls under the purview of machine learning. So there are many different kinds of machine learning styles and architectures. The previous one that was just mentioned is artificial neural networks. This is sort of the classic neural network most people think about. It's really good at pattern recognition and generation, and it's based on calculus and optimization theory. And you can think of it as it's creating a sort of like a very complicated mathematical function by learning from this real world data. It's almost modeling a hyperdimensional shape that exists beyond, beyond the third dimension and this multi-dimensional space. And it tries to massage or change the structure of this shape so that it adequately predicts or intersects with the data points that we're feeding into the network. Another popular style of algorithm is known as the probabilistic graphical models. And I've been working with these a lot lately, and they're a lot of fun. They're really good at automated reasoning, and to compare them with artificial neural networks, they are principally based on calculus and probability theory. And as such, what they do is they create really complex probability distributions by learning from real-world data. There are a lot of similarities between these two paradigms. They both use graphs, they both have this concept of nodes and arrows, and this direction of flow of information going from node to node. But the way that they calculate their values, the way that they calculate their predictions, and the way that they update themselves are very different between these two paradigms. I just wanted to show you, just introduce, a different paradigm so that you can kind of get an idea of the wide array of choices you have whenever you're trying to implement a machine learning algorithm. So for these artificial neural networks, the most popular way to update the weights is through a method known as gradient descent. And it does so, and then this method works by using this concept from calculus known as the gradient. And the gradient it's essentially a measure of how a function is changing. It measures the direction that a function is changing and the magnitude of that change. Now, the theory of gradients is far beyond the scope of this lecture. So I will not be going into how to calculate or build a gradient. Just know for right now that there's this thing from calculus called a gradient, and it measures how a function is changing, and we will use it in our machine learning methodologies. So let's say that we want this desired behavior, where we have an input of 3, and when we run this through the neural network, we get an output of 11. Now, let's say that we have a neural network that its weights were created or initialized through some means. Generally, in the field, the weights are just initialized randomly. You just pick a bunch of random numbers. So let's say that this neural network has already been initialized with some set of weights, and when we give it our input of 3, it in turn it returns to us an output of 7. And you can notice that this is not the desired behavior. The desired behavior is we want it to give us 11, and instead it's giving us the number 7. So what we can do is we take the difference between the desired behavior and the current behavior. Now, this difference between the two, it informs us of two things. It tells us the degree of wrongness of the neural network. The magnitude of how wrong it is, how far away its prediction is from the desired output. It also tells us the direction from the current output to the desired output. And then I give a couple of examples of if, say, the desired output is smaller, which is 11, and the current output is 15, the direction is negative. And then, as we just saw on the previous slide, if the desired output is larger, then the direction is positive. And you can see this relationship in the number line at the bottom of the screen, where green is the desired output that we want, and the blue node is the current output from our neural network. And you can see the arrows sort of show us the direction that we need to move our output so that it's closer to the desired output. So when we take this difference and we combine it with the gradient, it acts in this way that it informs us how to change the weights of the neural network. Specifically, the magnitude of the change to each of the weights that needs to happen, as well as the direction of change that the weights need to undergo. An important caveat to this is that it does not give a perfect change. It does not give us the exact numbers in order to achieve a perfect output. Instead, it just moves us closer to the desired behavior or the desired output. And as such, we have to repeat this gradient descent process over and over again until we achieve a level of accuracy that we're satisfied with. You can see this in this sort of graph at the bottom of the screen, where we start off with a difference of 4. We undergo a gradient descent step, and afterwards, we now have a difference of -2. And when we go through another gradient descent step, we then have a difference of 1. And so you'll notice that the signs of the difference have changed, but the magnitude of the difference is getting smaller. The magnitude has gone from 4 to 2 to 1, which means we're getting closer and closer to the desired behavior that we want to induce into our neural network. So the cool thing about neural networks is that they're very flexible. The previous examples I've been showing you is just it has a single output and a single input. Well, we can really we can use inputs and outputs of many different shapes. We can give it an input of a vector and an output of a vector of a completely different size. We can give it an input that's a matrix and get an output of a matrix that's also a completely different size. You could give it a matrix as an input and get a single number as an output. There's all these different ways that you can structure your network. Now, when we keep this in mind, we can realize that images are basically just three-dimensional shapes, or three-dimensional matrices. They have a width, they have a height, and then they have a depth of 3. 1 for each color channel, the red, the green, and the blue channel. And so we can thus feed images into neural networks and get images out of neural networks as the output. So a couple of basic image operations that we can do on a neural network. We can resize an image. That's where we're given an image that is very small with a very low resolution, and we can make the image larger, but we don't get any blurriness. We make the image larger, we increase the resolution without any loss of detail. The neural network is able to recover the lost visual information that happened when the original image was shrunk down. We can also animate images using these neural networks. If you've ever seen those Snapchat filters with the dog ears, or they give you the crazy cartoon eyes, or they swap your gender or something like that. That was done using neural networks. Well, mostly. Usually it's done during neural networks. I'm sure maybe a few of them are done through more deterministic means, but generally they're done with neural networks. Pretty much any sort of facial recognition stuff that nowadays is also usually done with neural networks. We can also add color to an image. So we can be given a black and white image, and we can spit out a 3-color channel image that recovers the colors that were originally lost. So some things to think about with all of this is that the quality of our output, or the quality of our neural network, is highly dependent on the data that we feed into the network. Every piece of data that we give it dramatically impacts the gradient descent step. Every data point can dramatically alter the way that the gradient descent works, and it can give you different outputs. It can change the shape that you're modeling in hyperdimensional space, and it can even give you completely different weights. just based on the data points that you feed into the network, or even the order of the data points that you feed into the network. So while humans are often outperformed by neural networks on many, many tasks, in order to achieve that level of accuracy, you oftentimes have to have very large amounts of both good and relevant data that you can learn from. It's not enough that the data is just good. It has to be relevant to the task that you're trying to accomplish. It doesn't matter how good the data is on traffic patterns in a city. If what you're trying to do is predict the weather, well, you're not going to get anywhere with that. Likewise, if you have a lot of relevant data, but it's not very good, you're not going to learn very much or have a very accurate model. Now, this really becomes important because after training, when you then put data into the neural network that it's never seen before, a network that's been poorly trained may give wildly inaccurate output. It may give you just crazy stuff that just doesn't make any sense. Now, this creates a sort of double-edged sword, because we can't possibly gather every point of data in the world. Because many problems can even have infinitely many different, manifestations of its data. And even if it's, if it is discrete, if there's a limited set of data, it may be on the scale of trillions and trillions of different possibilities. And we just don't have the time, the space, or the processing power in order to handle that. And as such, we have to learn how to make good predictions using the very limited data that we often run into whenever we're trying to train neural networks. So this sort of brings up this concept in machine learning known as generalization. When a neural network, after training, is able to accurately predict, it's able to give us good output, when we feed into it data that it's never seen before, data that was not in the training set, that it's the first time that it's ever seen this image. And if it's still able to give us good output or accurate output, we say that that network has generalized, or it's able to generalize outside of its training data. Now, this can also work in the opposite direction. Neural networks can fail to generalize, which is what we see happen here, where we were training a neural network to add color to a black and white image. As we saw here, we give it a black and white image as input, it's fed through the neural network, and we get a color image as output. And it's able to train and achieve some high level of accuracy based on that single image. Well, if we then try to feed in another black and white image that the neural network has never seen before, we don't know what the behavior might be. It might work just fine, or it might happen, it might do what we see that it's doing here, where it's got the shape right. It colored the face correctly in some of the clothes, but this blank background, it just had no idea what to do with. And so it just kind of freaked out and gave us a bunch of random data. And so we say that this neural network failed to generalize. Now, there are many reasons that can cause a neural network to fail in this way. I've harped on about how your data set can be too small. It's not given, all of the important data that it needs to learn from, so it can't learn the important relationships. It may also be because you give it bad data. And while it may learn how to work with this bad data really well, it can't really use the neural network on, good real-world data. Another cause may be that you just have a really poor architecture for your neural network. You could have made the neural network too small, and so it's not able to learn all of the relationships that it needs to. Or you could have made the neural network too large, and so it's constantly fighting against itself while it's trying to learn this complicated function that you've given it, essentially. Or, and this is what I see happen the most for beginners, is they improperly implement their gradient, or they improperly calculate their gradient. Which generally you probably won't even learn in the first place. Like your neural network probably won't even learn correctly if the gradient's properly improperly calculated. but it might, but it will just fail to generalize. So neural networks that fail to generalize, that fail to move and work well outside of this initial training data, we usually discard them because they're worthless. Like, what? They're failures. Why would we use this malfunctioning neural network to do a task? Well, I have a question. What is failure? Is this an example of failure? Because if you ask me, yeah, it didn't generalize, it didn't, give us a perfect coloring, but this image is still kind of beautiful. Like, it's still pretty cool looking. It got really close to the colorization that we wanted it to have. And honestly, I could see an image like this on display in some avant-garde art gallery. So, like, this begs the philosophical question of, like, how do we define failure? So I wanted to explore this topic a little bit. So I implemented a colorizing neural network, and I trained it using this top image right here. It's just a simple synthwave image that I scraped off the internet. And then I turned it black and white, fed it into the network, and then trained the network until it achieved something like, I think, like 96, 98% accuracy. And then in Photoshop, I basically traced the original image only in black and white using the brush tool. I got the broad strokes of the image. You have a sun with these lines, you have a sky with stars, you've got this grid and mountains and all of that going on. So it has a lot of structural similarities to the original image. And when I fed it into the neural network that, again, was only trained using this top data, well, it gives me this stunning output. I mean, it's obviously not correct. It's not, it didn't colorize it according to the original, the original color scheme, but it still gave this phenomenal, beautiful image that looks almost like a painting. And this image has a lot of the basic shapes. It has the sun, it has the bands on the sun, and it has the grid lines that are on the ground. And, we at the Katin Kollective actually liked this image so much that we turned it into our logo, just because we thought it was so cool. And so I actually repeated this process a couple more times, using a couple different, sets of initialized weights. And as you can see, I did the exact same process. I trained it on the exact same image. I gave it the exact same, input to test it with. But because I initialized with a completely different set of weights, I received this completely different output, which is still pretty stunning. And it still, gets the basic shapes. You've got the sun in the center. You can see the grid lines that are supposed to be there. It's got the sky now. And it's still able to do all of this, get really close to the general idea. And so I did it again. And we have another wildly different prediction. Just because I changed the initial weights that the neural network was created with. And again, it's completely lost the sun in the sky. It has this sort of dark area in the center, but you can see it still has the grid lines going on here. So it still learned a lot of the features of the original image, and it still recognized those features in the new image. It just wasn't able to generalize. It wasn't able to give us a much more perfect, attempt to colorize this image. So this, what happens if failure is desired? An example that I thought of just on the fly the other night was, if video game AI is too perfect, we're not going to be able to beat it. And that just wouldn't be fun. What fun is it to play against an opponent you can never beat, no matter how hard you work? And as such, it's preferable that we have an imperfect, but still relatively intelligent AI as an opponent. One that still understands the rules of the game, but isn't a chess grandmaster. in this chess scenario that we've dreamed up. And as such, we can control these various causes of degeneration, which is the failure to generalize. And by controlling these causes of degeneration, we can induce a more desirable behavior from the AI. And we can now create many different AIs with varied skill level, or the very levels of intelligence. And we don't have to implement, multiple different algorithms with different structures and different reasoning patterns. We can use the same, the exact same structure, the exact same algorithm for every single AI. We just maybe tweaked a few parameters that can control this degeneration. So this leads into the project that I was brought on board for. A local band in Dallas called the Children of Indigo, and I would like to point out that that is children with two L's. They are not children, they are children. So the Children of Indigo, they needed a music video for a new album that they were releasing. The brand of their group is like a psychedelic, trippy art style. Think like Beatles, maybe a little bit of glitch art, and as such, degenerative art seemed like it made a good fit for their style. You can check out the Children of Indigo. They're on Facebook, Instagram, and YouTube. I've known these guys for about a decade now. They're really cool. They're lots of fun. They've been a mainstay of the Dallas underground music scene for years and years. I think the first show I ever saw of them was in some random guy's garage. They're really good. I'd recommend checking them out. Just, make sure to use two L's when you look up their name, because all of the spell checking that search engines and social media does now has kind of worked against the group a little bit. So if you look them up on YouTube, make sure to click on search instead for Children of Indigo. So before we get into the project, I just want to show you my tech stack a little bit. I'm using Python 3.7.9. I used Anaconda as my environment manager. I use the TensorFlow library, specifically the Keras library inside of TensorFlow, to handle the machine learning and neural network mathematics. I used NumPy, of course. If you're going to do machine learning, you need to use NumPy. And I also use the CUDA and CUDA-NN toolkits, just because they basically let TensorFlow operate on the GPU. And if you're a newbie getting into neural networks, take it from me, it runs a lot faster if you do your processing on the GPU. It just has to do with the nature of the math that you're doing. Just using a real simple Windows 10 Personal Edition, 32 gigs of RAM, 8 gigs of video memory in the video card, an i7 processor at 3.7 gigahertz, and then some additional tools like Photoshop, 3ds Max, and Sony Vegas. So, our problem statement. We need to create a program that returns a coherent sequence of images that we can then use as the video for the music video. This sequences of images, it must be visually interesting. We can't just take a pre-existing library and apply invert the images and call it done like we're 13 years old making our first video. It has to be a new or novel or unique look. And this unique look must fit the psychedelic brand that the Children of Indigo use. And as such, neural networks were selected so that we could exploit these properties of degeneration. So I came up with two basic architectures, or neural networks, for to handle this process. The first was an animator. It creates an animation between two images, and you can see the blue frames are inputs fed into the network, and the orange frames are the outputs generated by the network. So if you feed this a beginning and a final image of say a ball at the beginning of the frame and a ball at the end of the frame, The animator will create the interpolating image. It will create a ball in the middle of the frame. Then the other neural network I created was the colorizer. You give it a black and white image, and it adds color to it. So the colorizer was based on this architecture that I learned from this guy who runs this YouTube channel called Python for Microbiologists. And he basically came up with this architecture so that he can automatically apply color to the black and white slides or the electron microscope images that he takes as a part of his work. I have a bibliography at the end of this lecture where you can figure out how to find him. He makes really cool stuff. I definitely check him out if you're getting into neural networks. So you'll notice in this is the sort of the structure of the network, how it starts out with a very large image, and then we sort of make the image smaller, but we make the processing layer that operates on the image deeper. And as we get further into the network, that gets more and more pronounced, where the image gets smaller and the processing that we do on the image gets deeper and deeper. This is a very common pattern you see in pretty much all neural network video processing. And this specific pattern here, where we have it start, as a full-size image, it gets smaller, and then goes back out to into another full-size image. This is known as the auto-encoder-decoder pattern, where we have it, encode the data into a smaller set, and then decode the data back into a newer, larger set. And so this colorizer receives as input a single grayscale image, which, the images were of shape 1024 by 1024. And because it's a gray image, there's only a single color channel. And then as output, it creates a full color image of 1024 by 1024 with 3 color channels. It recreates the red, green, blue channels based on this black and white image that it's fed. The Animator neural network is a bit of a different beast. This one was pioneered by a team from Asia. They're also in my bibliography. Would definitely check them out. They did a lot of really cool stuff with this sort of animator neural network that they came up with. If you saw any of those YouTube videos a couple months back that were all, oh, this movie, but it's now been turned into 60 frames per second, that was done using this neural network, or this architecture right here that was, or in this research paper. So it works by, you give it a beginning image and an ending image, and then it processes each one independently using their own weights. Then the 2 processed images are concatenated together and processed together as a single unit. And then the result of this processing is then copied and sent to 3 different layers, and each of these 3 layers all have their own independent weights. And these 3 layers predict the 3 interpolating images between the final and the beginning, the final and the beginning image. I did tweak this a little bit. The original architecture described in the paper had it just predict a single image in between the 2. I wanted it to predict 3 between the 2 because I thought it would look cool, and I wanted to see what would happen. And that's a big part of science, is just experimenting and changing things, just to see what the results are. So this is an example of how the animator works. We give it frame 0 and frame 4, and then it gives back to us frames 1, 2, and 3 that occur between frame 0 and frame 4. Similar to the colorizer, these images are 1024 by 1024 resolution. An important thing to note about the animator is that it only operates on grayscale images. It only operates on images of a single channel. This is now, not all of them have to. This is just the one that I set up. Only operates on gray images, and this is actually important later. We will exploit that property later on. So for training the colorizer, we fed it a data set of about 900 images that were scraped from the internet. Literally just looked up the term psychedelic and then scraped a bunch of images, resized them to 1024 by 1024. The images were converted to gray and then passed to the neural network. as the gray images were passed as the input, and the original color images were given as the desired output, so that the neural network could learn to recolor these training images according to this psychedelic art style. And we achieved something like I think like 95% accuracy, something like that, maybe like 93% accuracy with this. Now, for training the animator, we fed it a dataset of 1,300 images from a classic Betty Boop cartoon, just because we wanted to see what would happen. The images of the cartoon were fed in sequential order to the neural network in chunks. So we take a chunk of 5 images, we'd split it up so that it would, we'd give the network as input the first and the last image, and then as the desired output, the middle 3 images, and then we'd have it move forward a step, and then this image now becomes the new first image, and then we make the next 3 the new desired output images, and then that process is repeated all the way down the line for all 1,300 images. I forget exactly what the number was. I think it was like greater than 90%. Like, it wasn't as good as the Colorizer, but we still achieved remarkable accuracy with this process. So, to generate the video, we need to feed input data into the neural network. And as such, we created a very simple 3D animation in 3ds Max to serve as stimulation for the neural network. And we explicitly set the frame rate of this animation at very, very low, at 4 frames per second. And this 3D animation was also a grayscale image as well. We set the frame rate so low because we wanted the neural network to be doing the actual animating. So stage 1 of our process is we fed the unseen input data into the Animator neural network. And this generated an animation of 3 images. As we can see, just from right here, this has very clear flaws. We can already see the fact that the animator has failed to generalize. We see that fact coming through. And we also notice that the frame rate is now around 16 frames per second, because this animation right here, these 2 images are still occurring in the same time segment, but now we have 3 additional images that we have to show as well. So necessarily our frame rate has increased. And you can see this is the output of stage 1. With these are the beginning and ending images, and then these are the predicted animation between the 2. Now, you will notice that this animation that it's creating between them is more of it's fading from one image to the other while keeping the shared, the highlighted regions, the shared regions between them highlighted and still active. This is just an example of how it failed to generalize. There are other examples where it actually animated the movement perfectly. I just wanted to highlight this to point out this sort of strategy that it came up with, because it didn't know how to animate this movement. So the neural network defaulted to this sort of fading effect here, which I thought was very interesting. Even when it's malfunctioning, it still got pretty close. And you can even see in this final image right here, it actually still moves the skull slightly to the right by the time that the final image comes around. So there is still some movement processing going on. So the next stage is we gathered the set of frames created in stage 1, and we fed each one through the Colorizer neural network. This, in turn, applied the psychedelic art style that we were looking for. Now, because no new frames are being created, we're just modifying the frames that already existed. The frame rate is still around 16 frames per second. And you can see this is what the animation looks like now, after we've ran it through the Colorizer. The Colorizer definitely implemented a really nice sort of psychedelic pattern. Like, you get all these nice hues, bright neon colors, really weird patterns that weren't there before. So now the next and final stage, which is a little complicated, had to be split into 3 steps. So the first step of stage 3 is we gather the set of frames produced in stage 2. We then split each of these frames into its component RGB channels, so that essentially we're creating 3 new images, each for each frame, based on, and each one is just the red channel, the green channel, and the blue channel. An important point about this is that because now all of these new images are single channel, they can be operated upon like a grayscale image. So what we do is we then run each of these, these image channels through the Animator neural network again, and we have the Animator neural network operate independently on each channel, so that it predicts the animation on each channel. Now, an important thing to point out about this is that by the nature of color channels, there will be slight differences between each of these color channels that we have right here, and you can even see that, where the red channel looks slightly different from the green channel, which looks slightly different from the blue channel. Well, this is important because this means that when we feed them through the neural networks, the Animator neural network, the resulting images for each channel will also be slightly different from each other, because we've given slightly different inputs, and thus it makes sense that they would also generate slightly different outputs. For stage 3, we then recompile these predicted animations together. So these outputs from the animator, from the animation, from the Animator neural network, are either the red channel, the green channel, and the blue channel are now all added together into a single composite image. Now, this slight difference in the channel animations causes really interesting effects in this final composite image, which you can already see is very different from the original colorization that we were given. This has also increased the frame rate to around 60 frames per second, because we've essentially added even more images than what we added in the first stage. And this is now what the animation looks like after it undergoes this final stage. I'll leave this up for a few seconds just so that people can take a look at it. You will have noticed, however, that this fading effect has become even more pronounced, and the interpolated frames have become even more malformed and even more psychedelic, if you ask me. And we can still even see that it is slowly moving this final skull to the right. So once again, there is still some motion processing, and there's still some deformation processing going on. The network just couldn't animate this exact movement. So where are we at now? 2 images have become 17 images. Gray images are now colored images, and 4 frames per second has become about 60 frames per second. So let's analyze these results. The Colorizer step gave us some really interesting patterns, and as I mentioned, it definitely fits that psychedelic art style and that color palette. I want to point out, however, that these colors we've applied, that the network has applied to this image, I mean, they're obviously not the colors of a real skull. A real skull is white. They are, and as such, these colors that we've applied to the image are simply reflections of the color fed into the learning algorithm. And the neural network has essentially hallucinated these colors that it learned onto this skull shape that we've presented to it. There are also some noticeable artifacts present. You can see these squares, these square shapes right here. And especially in the black, you can see like this sort of grid pattern in the black. This is likely from the upsampling that occurs in the neural network during that decoding step. And there are ways that you can address this upsampling and make it a bit smoother. We decided it was fine for now. A little bit of imperfection actually adds to the effect. Now let's analyze the Animator. As we clearly saw, there were many mistakes made during the animation. It's very malformed, there's lots of visible artifacts, but the gist of the motion is still present. There's still this general idea of that the animator learned that it's moving from this position to this second position. And there are even many other instances in the animation where it animated them perfectly, where it got the movement down just right. So, despite this limited training on this highly specific data set of a Betty Boop cartoon, this interesting emergent behavior has manifested where it's able to just get barely good enough. It gets really close to being correct. So this, as I mentioned, the animator was trained using only a Betty Boop cartoon. And as such, every concept of movement, every pattern of how an object changes its position, everything that the neural network comprehends, it only knows from watching a single cartoon. And as such, this limited data set has induced a degenerative state within the animation neural network, wherein it can recognize and correctly process some forms of movement, while other forms are essentially guessed, or it just tries its best, but it's not very close. So again, I want to contrast this with pure noise, which is just random. Here, there is a valid pattern and a valid structure, and as such, there are correct connections within the set of neurons operating within the network. It's just that not all of them are firing correctly, and not all of them learned all of the patterns that were necessary to animate in every single instance that we could possibly throw at it. So the final compilation, we take all of the frames, and we put them together in Sony Vegas with the music. And once the band approved it, we uploaded the video to their YouTube, and you can actually check it out right now. You just look them up on YouTube, and it's this video right here. I'd also recommend checking out some of their other videos. They're a pretty cool band, especially their video for Tomorrow Ain't Promised. This was actually this video was done by a really famous, world-renowned puppeteer who lives in Dallas, and I think he did a really damn good job on the video. So once again, when you look them up, there are 2 L's in children. So just keep that in mind. Spell check has not been kind to them. So in conclusion, this intentional degeneration of neural networks, it demonstrates a new avenue of approaching tasks which require imperfection. And this degeneration, it can be achieved through a variety of means. Creativity is key here. I mainly used changing the structure of the network and limiting the data set to a highly specific input. But there are many ways that you could go about degenerating a network. You just need to identify them and figure them out. So this algorithmic degeneration, it's analogous to hallucination in humans. And as such, we're collecting the dreams of robots in the pursuit of visual beauty. And again, there are 2 L's in children. I really need to point that out. 2 L's. They are the children of indigo. So, if you liked this presentation, go ahead and look up Katin Kollective. We're on Facebook, Instagram, and YouTube. I will be publishing a recording of this lecture to YouTube later tonight. I will also be, in the description of the video, I will have a link to this set of slides. I don't have any of the code that I've created uploaded to GitHub. If there's sufficient interest, like if people want to see the code that I use, I'll be more than happy to upload it, but I don't feel like dealing with that right now. So if you want the code, just reach out to me. Or reach out to the Katin Kollective. You can, if you look up these slides, you'll also see the shapes of the neural networks that I used, just in case you wanted to recreate them or learn from them. You can find them here. This was the bibliography. These are the works that I cited and who served as inspiration for the neural networks. So let's go ahead and open up the floor to questions and answers. I'll go ahead and stop the recording.